Hey everybody, welcome back to our little series on vertex operator algebras. The vertex algebras can be thought of as representations of affine algebras that will act on modules. So before building these representations, we'll first need to discuss the relevant affine algebras. And to that end, today we'll explore arguably the simplest case, the one associated to sl2. Who has its own unique and perhaps frustratingly high level of internal symmetry, and will play an important role in the construction of the moonshine module. So buckle up and get ready for some technical details. We begin with the general case, sl2F. Let's define sl2F as the set of n by n traceless matrices over the field F. For some matrix A in that set, the vanishing trace makes for a considerable simplification of its characteristic polynomial. Notably, the eigenvalues of A do not vanish, provided that the determinant doesn't either. In other words, A is invertible. Since all we've demanded so far is the vanishing of the trace, the dimension of sl2F is given by 1 less than the number of matrix elements, that is, n squared minus 1. Now, let A and B be matrices in sl2F. We can, as usual, form a Lie bracket using matrix multiplication. By the cyclic property of trace, the trace of AB equals the trace of BA, and so the Lie bracket of any two such matrices is also traceless. Hence, sl2F is a matrix Lie algebra. To finish our quick discussion of sl2F, let's define an inner product. That is a symmetric bilinear form, which is given to us again by the cyclic property of trace. We now specialize to the case of two dimensions. As a vector space, the set of two-dimensional traceless matrices has dimension 3. Let's define an explicit basis for this space. The most straightforward basis involves one diagonal matrix and two off-diagonal ones. That they form a linearly independent set is hopefully intuitive. Today's first claim involves the Lie bracket of these Chevalley basis elements, and the second claim involves their inner product. Note that this is clearly not an orthonormal basis. Since today will be full of technical details, you might pause here to verify these simple claims by direct computation. Now, some simple Lie algebra remarks. First, the Cartan subalgebra, the maximal torus, or the maximal linear independent set of diagonal matrices of sl2, is really only one-dimensional. sl2 is the simplest of the simple, after all. The other two elements are root vectors. For the or under-initiated, these are the main components for the structure of all simple Lie algebras. Because it will be convenient in what follows, and perhaps more familiar to physicists like myself, we'll explore a different basis for sl2F. To that end, let's define the so-called sigma or Pauli matrices, sigma 1, sigma 2, and sigma 3. Note that the diagonal matrix sigma 3 is the same sigma in the Chevalley basis. We'll use both notations interchangeably. The next claim to verify is that each member of this basis squares to the identity matrix, meaning that they are their own inverse. Please verify these facts as an exercise. Note that this claim implies that, with the help of the inner product, the physicist sigma matrices form an orthonormal basis for sl2F. Our next claim involves the various commutators of the elements of this basis. Namely, the structure constants of sl2 are contained within the totally antisymmetric object with three indices, epsilon, I, j, k, which of course is unity if I, j, k is 1, 2, 3, and is antisymmetric under any permutations thereof. There should only really be 3 calculations to demonstrate this fact. Now let's have a little fun. Let J be given by I times sigma 2, and consider this span over the reals with the identity matrix and J. We claim that this vector space is actually isomorphic as an algebra to the field of complex numbers. Hopefully this is a fun little thing to prove. Aside from having a matrix model for the imaginary numbers, what makes claim 5 fun is its slight generalization. Define the matrices I and K in analogy with J. We now claim that the real span of the identity with I, J, and K is isomorphic as an algebra to the quaternions, which again you might verify as an exercise. This form of the quaternions is particularly important to physicists as their imaginary parts form a nice representation of rotations in 3-dimensional space. Stacked together with the identity matrix, they can be compiled to form representations of the 4-dimensional space R13, which is kind of like R4 but with mixed signature for its fundamental form. In other words, spacetime. We remark that the root vectors of the Chevalier basis, sigma plus and minus, are really just complex linear combinations of sigma 1 and sigma 2, or if you like, combinations of sigma 1 and j. Involutions play an important role in our discussion of vertex algebras, and the involutions of sl2F are manifold. Indeed, we claim that each of the physicists' sigma matrices gives an involution of sl2F by conjugation or similarity transformation. Proof. Let A and B be matrices in sl2F, and let A prime be A conjugated by some fixed sigma matrix. Since all sigma I are their own inverses, this simplifies. We can compute the product AB prime and simply insert a pair of sigma I between A and B, as it is merely the identity matrix, which means that the conjugated matrices satisfy the same matrix algebra as you might have expected. Moreover, conjugating A by sigma matrices twice brings you back to A, and so we're done. Note also that the inner product is invariant under conjugation, so conjugation is an isometry. Okay, that was easy. Let's get into the specifics of these involutions. First, let's explore the conjugation of the Chevalier basis by sigma 3. Our claim is that sigma, the diagonal element, is even under conjugation, but the roots are odd. Given that the first case is basically trivial, this is a straightforward computation that you might verify to get some practice multiplying these matrices with each other. Try to prove both cases with a single computation. We note again here that sigma, the diagonal element, is even under the involution. Next, we'll do conjugation by sigma 1. Here, our claim is somewhat more nuanced. First, the diagonal element sigma is odd under this involution, and second, the involution flips the root vectors. This is another pair of straightforward computations that you might consider doing. If you haven't noticed by now, the behavior of the diagonal element under involutions is going to play an important role in later discussions. It's also worth remarking that the behavior of the root vectors is mixed under the involution by sigma 1. To untangle things, we take even and odd combinations of the roots, which are just the familiar matrices sigma 1 and j. The commutation relations are also straightforward to verify. For fun, you might try to perform the same conjugation by sigma 2 and see how the involution works on the Chevalier basis. We now turn our attention to the Affine Lie Algebra sl2F and its twisted version. To construct the Affine Lie Algebra, we begin with the Chevalier basis for SL2. And as we've discussed in the past, this basis expands to include polynomials in the formal variable t, as well as a central element c. Note that twisting by sigma 3 means that those elements associated to roots, which are odd under the involution, pick up half integral powers, which are also odd under the generalized involution. The commutators for this affine Lie algebra are computed as before. C is of course the central charge and extends the otherwise commutative elements based on sigma when their gradings are equal and opposite. The commutators with roots are as you'd expect from the simple case, with the additional central terms extending the commutator of the roots. The roots with themselves, of course, vanish. Twisting by sigma 3 merely changes the grading of the algebra, meaning these algebras are essentially isomorphic, although not grading isomorphic. This is the significance of having a Cartan subalgebra of sl2 invariant under the involution. Indeed, sigma is trivially even in the untwisted case, and non-trivially even in the sigma 3 twisted case. This implies that the subalgebra of both affine algebras, given by the span of C, together with sigma times some non-zero powers of T, is a Heisenberg subalgebra. Moreover, it's essentially the familiar Heisenberg subalgebra H sub Z we discussed in Chapter 1. Note that we can and will append the degree derivation to these algebras in the usual way. Finally, we consider the slightly more complex case of the Affine Lie algebra sl2F twisted by sigma 1. Here again, we start with the Chevalley basis, but rotate it to a slightly different basis, which we know is manifestly even or odd under the involution of sigma 1. The twisted affine algebra is then comprised of the span of elements including the central extension C, half integral graded elements are based on sigma and j, and the integral elements are based on sigma 1. The commutation relations are a little more complex in this case. The intuitive ones, those whose powers of T do not vanish, essentially, are given here. And those subject to central extensions are presented here. Remember, the terms with central extensions are proportional to the symmetric bilinear form on sl2F. We close with a final remark. Just like the other cases, sigma 1 twisted affine Lie algebras has a subalgebra spanned by C and sigma with formal powers of T. In this case, of course, they are half integral powers. This is essentially the Heisenberg algebra H z plus 1/2 studied in Chapter 1. Importantly, this is a different Heisenberg subalgebra than is present in either the sigma 3 twisted case or the twisted case, again, owing to the odd nature of sigma under the sigma 1 involution. A final exercise worth exploring is applying the formal series methods of Chapter 2 to the commutators of all three affine algebras studied today. We'll be primarily working with formal series moving forward, just to simplify things. I'll include the answers to these exercises in notes that will accompany the show, so please do check out the description below for a link. And that's our show. Next time, we'll begin our study of twisted vertex operator algebras by expanding the Heisenberg subalgebra of the sigma 1 twisted SL2 to a module for the entire algebra. So, see you soon.